Thank you very much, Jill, and thank you all for coming. What I plan to do is a sort of historical tour through some of the things that have been of interest to myself and my research group over the years. I'm going to try a few demonstrations, so bear with me. If they don't work, I've got the slides to back them up. And there will be some group participation from the audience, so don't try and settle too deeply in your chair because you'll need to get up and move around a bit. Okay, perhaps the most important thing I need to do this evening is thank the people involved in getting me to where I am now. You may be able to read your own name there, certainly some of them in the audience. Yes, there are a lot of people that I've been involved with. Quite beside then family, friends and colleagues. These are some of the people that I've collaborated with, and at the bottom are some of the people who have managed to convince me to give me some money to do the things that I enjoy. Okay, having said that, I want to start off with a disclaimer. Some of you may have read The Restaurant at the End of the Universe. It's a book by Douglas Adams. It's part of a trilogy in 5 parts. This is the second book. And it claims that, as you can read, that although it can't be informative or useful about everything, it plans to be definitively inaccurate. So I've applied this to myself. So this evening, I'm planning to be definitively inaccurate about everything I can as possible, and we'll go on from there. So I was once asked, when I was going through US Customs on an occasion, what do I profess? So rather than a list of things that I'm going to talk about this evening, these are the things that I'm going to touch on. So in terms of the polymer behavior, I'm going to touch on why size matters, how shape matters, and ultimately then how the rate of things moving also matters in terms of the behavior. And these are all things that we've looked at one point or another and are continuing to look at nowadays. So I just wanted to start off with some etymology, and really brings me back to why the title of the talk was Polymers. It's all ancient Greek to me. For those of you who are in the polymer world, of course, this is all very relevant and you know all about it. But for those of you who don't know why polymers are called polymers, hopefully I'll have convinced you why during the rest of the lecture. But the origin of it comes from a Greek, or ancient Greek really, terms meaning many and a share. And that gives you the word polymeros, meaning having many parts. And that's what polymers really are. They're materials that have many parts to them, and really that's the reason that they are so interesting. They are a collection of molecules bound together covalently that have very interesting properties that you can't obtain from other materials. Now, polymeros was used up until about the mid-19th century, and then clearly the Germans got frustrated by the terminology and Germanicized it into polymer, and that's the word that we carry forward nowadays. So we now know where the terminology comes from. So I just wanted, for those of you not polymer chemists, I just want to give you a master class in polymers, or at least a beginner's class. Polymers 101 for the beginners. Now, although I'm in a chemistry department, I'm going to do this from a physics point of view. And for the physicists, they don't really care what the chemistry is. They're just interested in how things work from sort of generic point of view. And to make a polymer, you need many molecules, and that's what we've got on the left-hand side, a collection of molecules, small molecules. And what you do is some chemistry, and if you're good enough, what you end up then with is a long chain of these molecules bound together to give you a polymer chain. And it's the chain itself then that gives rise to what we know as a polymer. So now you can see where the terminology comes from. It's a material with many parts, so polymers. So I want to talk about size to begin with. And the size of a polymer is quite an interesting and somewhat subjective viewpoint. So what is the size of polymer? It's a bit like asking somebody how long is a piece of string, because if you ask different communities, you get different answers. If you ask the chemist, they tell you what the molecular weight is, because chemists love to know precisely what they've synthesized. The physicists try and avoid understanding the chemistry and really want to know something about the behavior of the system, and a lot of it can be related to the number of units that you have in the system rather than actually the chemistry. And the engineers really don't care what the physics or the chemistry is about, they just want to know how to process it. So their terminology now reflects that, and they talk about then the polymer size in terms of the melt flow index. It all means the same thing ultimately. You're trying to determine the size of the polymer and the shape of it in some extent. So the molecular weight, degree of polymerization, the melt flow index, it doesn't really matter. You're still trying to capture the information of what the molecule is that you've synthesized in your pot. Now, what you end up with is effectively molecular spaghetti. And often we talk about this as an analogy to try and get undergraduates to understand what polymers are in terms of their behavior. And polymers can exist in many different states. In the solid state, they can exist as rigid molecules which can crystallize, or they can exist as states that look like the bottom left-hand corner, an entangled mess of polymer chains. And so we can have, on the bottom side, amorphous chains. On the top right, we have crystalline states. And of course, we can have mixtures of the two. Now, the reason that the spaghetti is quite interesting because it brings into lots of context some of the behavior of the polymer in terms of things like entanglement, which you'll see later will become quite important in terms of mechanical behavior. And you've all experienced this if you've ever eaten spaghetti. If you shove a fork in it and try and pull out one of the strands, it's actually quite an involved process because you lift off ultimately quite a lot of the spaghetti rather than just the one that you're interested in. And that's the entanglement effect. Now, we all know that to get around that, you chop it up into small lumps. So you go below the entanglement molecular weight, and it becomes a very easy process then. Now, the other aspect about spaghetti is quite interesting because if you think about it, it does look like what would happen if you could get a microscope and zoom in on these molecules and show them at very high magnification. Now, if we do a simple analogy and we assume that this spaghetti then is a polymer chain, let's assume that the spaghetti is 1 or 2 millimeters thick. What would then be the average length of the spaghetti that you would produce in your chemistry? Now, a typical polymer would have a molecular weight or a degree of polymerization of 10 to the 4. Very high molecular weights would be 10 to the 6. And so your aspect ratio would go from 1 to 10,000 to something like 1 in a million. What does that mean for our piece of spaghetti? Well, it would mean your piece of spaghetti would be 1 or 2 millimeters diameter, but it would then start something like 20 centimeters long if it was a short polymer, and something like 2 kilometers long if it was a long piece of spaghetti. Now, you can imagine then trying to twiddle a 2-kilometer piece of spaghetti to actually get one single strand out of your spaghetti. It's much easier trying to get 20 centimeters because that's just a few turns of your fork. And so this really does demonstrate some of the factors in terms of the behavior that get this massive range of property differences based on just molecular weight and nothing else. So this is why the physicists love counting number of units rather than actually worrying about the chemistry too much, because you can actually understand quite a lot of the physics of the behavior just simply knowing how long and fat the chains are. Now, you can see how that length effect can apply to things like mechanics. And the example that you've all come across around the house are the differences then between a candle and a plastic bottle. Now, plastic bottles, for many instances, are actually made from HDPE. So these are things like your bleach bottles and water bottles occasionally. Those are quite strong. They don't tear or puncture or rip, and you can actually hold quite a lot of material in those. You'd never make a bottle out of wax. It's actually very poor mechanically. Now, they're actually chemically identical materials, and all you're doing is changing the length from a very short chain to one that's much longer. And so mechanically you go from something that's very weak and brittle and quite useless mechanically to something that's very strong and of extreme practical use. As I said, we're just changing the size and we're not changing the weight. Now, one of the things that we looked at some years ago, and we still play around with this in terms of trying to understand the process of interactions of systems, is a process of called diffusion. Now, this was actually looked at in great detail by some very famous theoreticians in the field, Doyen Edwards based in Cambridge and De Gennes based in Paris. And they came up with a theory that is associated and with what is known as reptation. And they chose reptation because they took the analogy of the behavior of a polymer to be that of a snake, hence the cartoon in the top right-hand corner. It wasn't just some arbitrary thing I just threw in there. Now, if you think about the way a snake moves, it can move very easily along its length, but it has immense problems moving sideways because of its length. Because if it comes up against an obstacle like a branch, it can't go through the branch, it has to go around the branch or past the branch by moving through its contours. And that, in a nutshell, is the principle of diffusion. So what I've got here is a cartoon of many polymer chains in an amorphous system. And one of the chains is colored blue just to highlight it. Now what you can see is these chains are quite tied together. And so the blue chain, if it wants to move anywhere, the easiest thing for it to do is actually follow its contour length. And so I've marked the head of it with the black dot on the top right. And if you leave it long enough, what the polymer is going to do is move along that entanglement just like a snake would through a dense field of brush or a tree or something. And you can see how it may then move, and the dotted line that you see on the bottom right is actually where it came from. Now you can see the tail has moved a little further and the head has moved to one side. So this is the process of reptation. And of course, you immediately see then that reptation is related to the number of units, i.e. the length of the chain. And so if the chain increases in length, it's going to take much longer to diffuse anywhere. So the theory is actually very relevant to all sorts of applications, and particularly in processing and things like bonding and interfacial tension and so on. So at this point, I think what we're going to do is a little demonstration in the room. I've always wanted to do this, so this seems the perfect opportunity. And we're going to try and see whether we as a unit can actually reptate, and we can see whether we prove De Gennes' theory of reptation. Okay, so Mark, and let's say 5 of you, if you can stand up in that row. Okay. And then all the rest of the row plus the one behind, if you can get together into one row. Yep. You as well, Georgina. If you shuffle down a little bit. Yeah. Okay. Ian, you can join in. You're suitably suited up. Okay. So, sorry, I've forgotten your name, but if you join hands with the 5 people on your left, if you will all link hands. Okay, you're a chain of 5 units, and then the rest of you, those 10 people, 1, 2, 3, 4, 5, 6, 10, you link hands. Yeah, Georgina, link hands. Okay, when I give the command to go, what you're going to do is move out of your area, and I'm going to time how long it takes this gentleman here to get out, and how long it takes Mr. Hello to get out of the system. Okay, so we've got 2 chains now, reptating. And they're going because they're confined within their system. So we've got the confinement sorted out. Okay, how do I work this? Anybody got a stopwatch? I don't know how to use my own watch. Oh. Okay, right. Let's go. So that was 6 seconds. Keep going, keep going. So that was about 16 seconds. Okay, so we're not quite rotating correctly. What we should have found, you can, you can get back together. So it proved my point. It was worth a try. So the theory suggests that the time that it takes for a chain to move should move something like the number of units cubed. So what we should have found is that the shorter tube should be moving 8 times faster than the longer one. Maybe we should actually try it with more people in the audience. No, we don't have time. So if it worked correctly, and we'll assume then that we had different process going on there, you should be moving 8 times faster than the group on the right. Okay, so that's rotation. And thank you very much, everybody, for helping disprove the theory. So, what I want to talk about is shape. Shape in the broadest sense. And in terms of the shape, I'm playing around here with systems that are no longer perfectly linear, but now have branches. Okay, so here's how you do it in terms of the physicist's viewpoint of making a branch chain. You take some monomers that you had before and you throw in a green one, which now allows you to add in something on the side. You do some different chemistry this time and something happens and you get a system where you have a branch off the side. And the branch can be different lengths, and of course it can be, I've drawn it with the same monomer as units, but it could be a different one if you wanted to. So these branches are actually very important because if you think about our spaghetti analogy, it's easier for pulling a single piece of spaghetti out because it's nice and linear. If you tie another piece of spaghetti to it, now you've got a difficulty of having this extra bit hanging off the side to actually move. So that extra part, the branching, actually changes the property quite dramatically. And we'll show an example of that and how that changes in a minute. Now, the other thing we've spent a lot of time looking at are copolymers. And copolymers are literally at least 2, if not more, polymers that are chemically bound together by a covalent bond. So from a physicist's point of view, we have a blue and a red chain added together. And the chemical covalently bonded systems then mean that they have very interesting properties because they capture those of the blue chain and also of the red chain simultaneously in the system. So what have we been doing with those systems? The first one is to look at surfactancy. And here we're going to have a little demonstration. So I have to change, because if I get chemicals on here, my wife will kill me. So what I'm going to try and demonstrate is then how polymer surfactants work in exactly the same way that they do in your kitchen every day. Well, assuming you do the washing up every day. And so I've got a few things down here. Quite a few things down here. And what I'm going to do is take 2 different polymers and I'm going to mix them together. Now, what happens with many systems are thermodynamically, polymers don't like each other typically, so they don't mix. They have similarity, therefore, with things like oil and water. And what you can do is add a polymer surfactant, and you can see how the cartoon shows what happens. And so this is just in case the experiment doesn't work. But you can see on the left-hand side, this is the polymer, the homopolymer. So it's a linear system of the red chains, and on the right-hand side are the blue chains. They don't like each other, and therefore they're not mixing, and the interface is very sharp. What you can do is add the copolymer, which is a mixed system which is covalently bound of blue and red chains. And what it does, as you can see from the cartoon, it stitches those 2 together. So there's a mechanical interaction, and it locks the system and changes then the properties of the system overall. Okay. So we've got a blue polymer. Got a yellow one. Sorry, I couldn't get a red one. But this is a very special one because it's made by Felipe, who's in the audience. And we have our surfactant. So what we're going to do then is mix a bit of these two together. These are polymers that don't like each other, so as we anticipate, these won't mix. So what we can do is put a bit of this yellow stuff in here. Okay, a bit of that. And what we need to do is add a tiny bit of this blue stuff. So this is the other polymer. I'm only going to add a little bit, otherwise the effect gets a little bit difficult to see. Now, you won't actually see what I'm doing so much, except when I start emptying this onto the slides. So I still have some chemicals left in the lab, by the way. I didn't bring everything with me. Okay, so I'm going to add surfactant to one side. Those who are close enough will see what I'm doing. Okay. And I put some lids on. And what I'm going to do is shake them up and then put them onto here so you can see the effect of adding this polymer surfactant to the system. So I'm going to zoom on here. And hopefully that will focus in a second. Yeah. Okay. So on the top, I'm going to add a system of two polymers that don't like each other. And so you can see I'm shaking. It's not a trick of my hands here. And I'm going to put it on here, and you can see, hopefully then, a system that is yellow with a bit of blue in it. And you can hopefully see that the blue is starting to separate and recombine then into bigger and bigger droplets. So initially when I shook it up, the droplet size decreases just through mechanical separation. And I didn't put very much in, but you can see the effect now of the system working. So now I'm going to take the surfactant one, at least I hope it's the surfactant one, and I do some shaking. And now I add it in the same way to the slide that we had before. And hopefully you can see it's gone slightly green, which is good because what we're doing essentially is mixing a blue and a yellow color. So it's a visual indication that we're getting much better mixing. It's never still going to be perfect. We're not going to get molecular interaction on this level because still the blue and the yellow polymers really still hate each other. But what we've done is we've added the surfactant, the polymer surfactant to the system, and it's stabilized then that interface. So these small droplets can't then grow again because they're surrounded by these surfactant chains. So these are very important. And these are used in all sorts of different areas that you find even around the house. A very common one, and one that actually my father became quite famous for, is something called high-impact polystyrene. In fact, my friends actually termed him Professor Hips because of that. But it's actually used extensively in things like the insides of fridges. And high-impact polystyrene is a polystyrene, which is the blue, and the red in that case is actually an elastomer, which gives it then elasticity. And those two polymers hate each other. They can't mix. And if you don't put the surfactant in, you get the top behavior, and it's mechanically useless. But with the polymer interfacial compatibilizer, you get the bottom effect, and it's mechanically a very good material, and is used, as I said, quite extensively. So we spent a lot of time looking at these materials, not only just because of their compatibilization effect, but also trying to work out how these things actually get to interfaces. Because if you add it to the surfactant to the red region, the blue parts of the chain don't know that the blue chains are there, so how did they actually know to move to the correct interface? So we spent a lot of time looking at these types of behavior. Okay, well, we can leave that running as we go through. Now, the other thing that you can do with block copolymers, and this is some work that we're continuing with my colleagues at Georgia Tech, is to try and address the issues associated with beating Moore's law. And I don't want to go into this into too much detail because many of you are familiar with this, but essentially Moore's law is a way of describing how many processes that you can fit onto a given space for improving then the performance of computers. And as you can see, the chart change has been increasing over the years. And the problem has come now because typically before they've been using sophisticated templating to actually produce then these very small structures. The cost of that templating system increases very dramatically every time you want to decrease the size of the features that you want to put on. So myself and my colleagues are looking at systems like block copolymers to try and beat this so-called sub-15 nanometer space limit. What that really means is, can we fit even more chips on your computer and make them faster than they currently are? And can you do it in a way that people actually can afford to buy the chips that you've now made? Now, as you can see, we can process polymers amazingly easily and very simply. And if you make the right polymer, and the copolymer specifically, the polymer actually phase separates, so the blue and the red want to get away from each other, as I said before. The covalent bond between them prevents that happening, and they form, depending on the amount of red and blue in the system, these beautiful, elegant structures in the solid state. And what we use these for are then templates for which we can do the nano patterning into the microelectronics. So the problems are more than this cartoon suggests, but essentially you can very easily get block sizes now that are very clearly much less than the 15 nanometers. So essentially by doing no more than I showed you just now, by mixing a few things together and pouring them out and making a layer, I can do what Intel now currently do with fabrication facilities that cost billions of dollars. Okay, so I don't have time to talk about this in detail, but you can see that the copolymers have a very different avenue than just mechanical stabilizing. Now, another thing that we've been looking at quite extensively is also block copolymers as hydrogels. Now, what are hydrogels? Well, the cartoons at the bottom tell you, in some sense, you take a chemical structure that actually likes water, and you add water, which are the blue molecules, and the hydrogels are slightly cross-linked so they don't fall apart, but what they do is absolutely love water. So they're going to try and grab as much water as they can in the system. And I'm going to demonstrate that with something. This is actually familiar to many people who have young children, because this is the same kind of thing that you'll find in babies' nappies. Does anybody wear contact lenses, soft contact lenses? Okay, it's the same chemical. So you're wearing nappies in your eyes, or babies are wearing soft contact lenses. Either way, it doesn't matter. Okay. So this stuff is a hydrogel. Now, what you can do then is add water to that, and it's going to absorb. Now, I've chosen this one specifically because it's very fast-acting, but not all of them are fast-acting. And we come back to ones that we worked on which are specifically non-fast-acting. And this is just colored water. But you can hopefully see the fact that the water isn't spreading. You can see how much it's absorbing. So this is actually an interesting one. It will absorb something like a few hundred times its own weight in water. So you can still see, hopefully, that there's completely unreacted material, because the stuff in the middle still wants to absorb more and more of the water. So you can't quite see it, perhaps, but if I hold it up, maybe at an angle, you can see that it's swollen significantly. And in fact, I can do this a little bit more, faster and faster. And you can see how it absorbs the solvent. So, hydrogels, of course, people use them for all sorts of things. We were working with a team in Oxford who were particularly interested in cleft palates, and that's the picture at the top. This is actually an acute cleft palate from a young child, but typically the doctors are trying to solve the clefts at a very early age because a cleft actually prevents babies suckling when they're young. So it requires a lot of intervention if you don't treat them quickly. And the solution to improving the cleft palate surgically is actually quite crude. What the surgeons do is cut down the gum line on either side and actually just pull the two bits of skin together and stitch it up in the center. So it sort of works in small clefts, but in these acute ones it doesn't work at all. And so what they want essentially is more skin. Now, skin grafts have also been known about for a long time, but you can't graft external skin into a mouth because every part of the skin externally has hair follicles. So what they don't want to do is stitch in a new bit of skin that they've scavenged from somewhere else, and then in later life when they go through adolescence, start growing hair on the inside of their mouth. So the solution is to, that we're working towards, was these hydrogels. And it's exactly the same action that we saw here, and you can see now it's absorbed quite a lot of the fluid. So you can see at the back, hopefully, then, how much it's swollen. And it still will take more. What we do, as the picture shows in the top right, we make these hydrogels, and we engineer them very carefully so that they only swell in one direction rather than in all directions. So what the surgeons do then is insert the unexpanded hydrogel into the mouth. This expands outwards, and they place it between the two gaps in the gum. It expands outwards, and if you do it slowly enough, the skin will actually regrow to accommodate the new growth of the hydrogel underneath. If you do it too quickly, so if you stuck in this the nappy gel, it would expand out too quickly, it would restrict all of the fluids and the blood getting to the skin, and it would die very quickly. So you have to do this expansion over some months. This is why I didn't choose that one to demonstrate hydrogel expansion. Otherwise it would be a long lecture. But you can see the expanded version on the left-hand side has expanded many times the original one. So we spent a lot of time engineering these things, and it was actually taken up by one of our co-workers and has formed this company that now sell these things commercially for all sorts of surgical applications. But a very nice application of hydrogels nevertheless. Okay, so we come to the case of the humble plastic bag, and you may think these are the scourge of the world at the moment, but to people like Exxon, who we were working for at the time, these are big business. So plastic bags is just another name for packaging of plastics. Packaging plastics make up by far the biggest majority of all the plastics that are made on the planet. And in fact, something like, well, anybody would hazard a guess how much plastic is made per person on the planet annually? Not you, Anna, I'm sure you know. Anybody? A kilo? Who thinks it would be more or less than a kilo? 10 kilos? More, yeah. So it's something like about 37 kilos for every man, woman, and child on the planet. And of that, about a third of it is polyethylene. So for Exxon, who makes 80% of all the polyethylene in the world, it's actually a significant fraction of their business. So they're keen to understand and control polyethylene. Now, polyethylene sounds just a very simple molecule, but it's not. And it's not because it's really, in many cases, a copolymer. And the copolymer is built with a backbone which is just purely carbon and hydrogen, and then you add in branches. And it's the branches that give it its properties in terms of the packaging material that you want. And for packaging, the two things you don't want to happen when you stick in your groceries when you go home at night is the thing will puncture or tear. And so if you get a bag that is tearing or puncturing, then it wasn't Exxon plastic that we worked on. So the question everybody wants to know is, where do you put the branches and how many do you put in? And that's still an open question, but in the research that we've been doing within the last 7 to 8 years, we're getting much closer to the solution for that. And the reason that's important is because these polymers form what are called semi-crystalline structures. And that really means that we can get packing on a very local level. Those chains don't actually form crystals all through the structure. They also have amorphous regions, as this cartoon suggests, by these blue chains. And those blue chains and the red chains, the crystalline and amorphous regions, form these extended structures through space. So I apologize to the pure polymer people here. This is more of an analogy than a reality, but at least it brings the concept together. Now, when we pull a polymer, lots of things happen. And if we start off with the system, which is the semi-crystalline one above, you've got the crystalline regions and the blue chains, which I've drawn in as the amorphous ones. The amorphous chains, although they don't look like that because this cartoon only represents a very small region of the polymer, their orientation is random in space. So that's what those arrows represent. They point in all directions. Only when you start loading the system does the system actually respond. And you know when you pull a plastic bag, it actually starts stretching. What's happening initially is actually the amorphous chains actually starts extending and they align. Actually, it's much more complicated than that because also the crystals start changing as well. And actually they form different types of crystals, even though they don't macroscopically change their dimensions. But the alignment is very important. And then at some point, the crystals start breaking up, and then you get a different type of behavior that gives you the toughness of the polymer. Now, the reason that this is actually very important because of these is because of the branches. And in the expanded version in the top right, I've tried to show you what that really means. So these branches, it could be very short. They're maybe only as short as 4 carbons long, but they're too big to actually get into the crystals. And so when you're pulling, what happens is that the system will allow the chains to extend until you pull all of the branch points to the edge of the crystal. And at that point, those branch points start destroying the crystal. So they're essentially forcing the crystal to pull itself apart. So the control then of where you put those branches is absolutely essential to dictating the behavior of the polymer, because they then dictate the mechanical performance and ultimately the performance of the polymer that you're trying to address. So whereas before we started this work, there was no actual understanding of how that actually interacted. And what we've been able to demonstrate is actually the very small chains with the shortest distances between the branches actually, even though they're a very minor fraction of the total polymer in the system, they are actually dictating the entire properties of the polymer. And now, with that knowledge, Exxon can actually focus on making polymers in a more efficient manner using that technology. So we've also fairly recently become interested in the humble plastic bottle. I haven't advertised one, but this was actually work that started off being sponsored by Coca-Cola. And it was for a very good reason, because Coca-Cola World Headquarters is actually right next door to Georgia Tech campus. So it was very easy to work with these guys. Now, traditionally, as this shows, most of the bottles that are produced essentially come from oil. It's only within the last couple of years that the PET bottles that people have got, this young lady has got one, these are made, half of it is actually coming from renewable green sources, but predominantly it's oil sources that make up all of the plastics. The question then is, can you actually derive a plastic bottle or other packaging materials from plants or some other waste product that you can get as a renewable source? And we've spent a lot of time then working on developing new polymers that have the important properties for packaging. So they are, A, mechanical properties. So, of course, you don't want to put the fluid in and the bottle just flop about. But also, because it's packaging, you want it to actually prevent carbon dioxide getting out if it's a carbonated drink, and you want to prevent the oxygen getting in and spoiling the food. Now, what we've been doing is actually looking at different top polymers that can actually be derived from plants And because they're derived from plants, you can actually take them back to something that's renewable and a green technology. And so we started this work in Georgia Tech, and we're now continuing with one of my colleagues who's sitting in the audience at the back. So it should break the cycle from going from petroleum non-renewable sources into the landfill. And to give you some idea, these are numbers I collected before I left Georgia Tech, but something like 2 million PET bottles are discarded every 5 minutes in the USA. So you can see that the problem, if you can address this in an economical way, would actually produce a vast improvement in terms of the waste that is produced globally, not just in the US. Okay, let's think about rate then in the last few minutes. Rate, in this sense, I'm not talking about diffusion now, I'm talking about much faster things. Why is that important? Well, plastics are being put into environments that they were never really thought about previously. Of course, they're being used because they are low weight, they have strength, but they are being put into situations where potentially 50 years ago people may have never thought that polymers may go. And so, for instance, the 787, it's a very impressive plane made by Boeing, which is using extensive amounts of polymer composites. Lots of body panels in cars now are made from plastics. And so when these things are required to do their job, they need to withstand then all of the environment they see. That's also true in protective clothing, and a classic example with all the conflicts that are going on in the world at the moment are the bulletproof jackets. But that's equally true in things like the protective clothing now being developed for the elderly to stop them breaking things when they fall over. Now the point is that in these behaviors, and as shown by the car, these deformations can be very, very rapid but very short-lived. And the physics behind that is very poorly understood. Phenomenologically, people measure it and build in a massive safety factor because they can't predict the behavior. So we're particularly interested in this, and we all have experienced this to some degree, and because we are in the home of golf, so I'm told. I'm not a golfer myself, but I want to show two movies that I didn't actually take. They were freely available on YouTube. But what they show is the difference in behavior of deformation at different rates, and you'll see the difference this makes. So the first movie is somebody of the ilk of Tiger Woods at his prime, who could hit the golf ball very quickly, and you can see what would happen if you had a very high-speed camera when you... Oops. If I can get the movie to work. Okay, is it working? Yeah. Okay. So what you can see is, of course, the ball, it repays itself, deforms massively. And here it's a complete pancake. And it's only doing that because it's moving very quickly. And you can also see that it actually fully recovers, which is a good thing because you don't want it to fall apart every time you hit the golf ball. It could be quite a laborious game then. Now what happens then if you squeeze a golf ball very slowly to the same degree of deformation, and this is what's happening. This is now happening in real time, and you can see then that this press is going to try and compress it to the same degree that we had before in the previous one. And it has a very different behavior. Now it's the same golf ball. Okay, they call it, this one's a yellow, orange one, and the other one was white, but the difference is only in the rate. It's not in the chemistry or the physics of the system, and all we're doing is changing the rate of the deformation. Now, these can't be predicted in any way, and the very sophisticated engineering models that we use to actually understand the deformation that would predict this kind of behavior can't be used to predict the ones where you hit it at very high rates. So we're particularly interested in this, and this is going to be my last demonstration. What we do is we do a little bit of ballistics. So this is where it will wake up everybody who's been snoozing and get you ready for the reception afterwards. Okay. What we essentially want is a gun. Okay. This Might upset the microphones, but Andrew, do you want to come out and help me hold this? Okay, so this is my helper, Andrew. Thank you very much. Okay, so this demonstrates essentially how we're going to do the experiment. And what we need is some other bits in here. Okay, here's one. And we've had my wife building us impermeable end caps for weeks. These are her favorite flavor. So now you know why you've been eating so many, being force-fed crisps the last few weeks. Oops, need a bit of cloth there. What you're going to see then is how we actually perform these experiments in the ballistic state. Okay, that's your end. And what we're going to do is show you how a plastic ball, like a ping pong ball, will change its behavior when you fire it very quickly. So at slow rates, it can actually bounce very easily, and if I bounce it against a block, it bounces off the block. What we're going to try and do then is show you what happens when it hits the block at a much higher rate. And I need this. So okay, let's see if this works. Got everything connected. Pressure on. Okay. So I'm going to put earphones on. You may want to cover your ears in a second. Okay, give that a couple of minutes to warm up. But essentially this is the can't hear myself, Pete. You don't have to cover up yet. What we're going to do is show you the basic operation of the behavior. Now the reason that this works is nothing to do with chemistry. It's because the ping pong ball will only go to a certain velocity because of air resistance. So what we've got here is a vacuum that's just withdrawing all the air out of the vacuum tube. And so when I puncture this end, it's going to allow then the air will push then the ball down through a vacuum essentially. And hopefully, if we've done it correctly, it will come out at the other end and move that block a little bit. So we'll see how this goes in a second. So I'll do it from this way so you can see when I puncture it. So before I puncture it, you might want to cover your ears. Okay, everybody ready? Let's see if this works. So, we did move the block, and we do a little bit of damage to the table tennis ball. So, this may sound like quite a childish type of approach to chemistry. Well, it is really, but it does actually demonstrate some very important factors. Well, thank you very much. It does help us understand then the behavior, because we don't have the cameras fitted on here that show us the behavior at very high speed, which we'll need to interpret that. Couldn't fit everything in the trolley on the way down. But I've got a couple of cartoons showing what happens then at very high speed to these different types of polymers and the kind of things that happen to this. Now you can see this is deformed because it was moving at high speed, and its behavior then is very different from what you saw when we're bouncing it on the desk at a lower speed. Okay, so at a lower speed, the polymer just bounces and doesn't do anything very much. So what I'm showing here, I'll play it again. The black section on the right-hand side is just an immovable object. And this long object here is actually the polymer that we're shooting at the system. So this is slowed down high-speed imaging. So these images are of order about 1 or 2 microseconds in length, just slowed down so that we can see what's happening. And this one is firing at about 200 meters per second. And you can see then that it deforms and it bounces back. This one is the same polymer. Well, it's a different sample, but made from the same polymer. This is going at 300 meters per second. You can see it deforms much more. And you get a nice way of making golf tees. And this one is moving at 450 meters per second. And you can see that our golf tee turns into a mushroom. Now, the interesting part about it is, it's not that people haven't observed this, it's just that nobody understands why it does that. So what we're trying to do is actually follow up this work and actually try and build smart materials that actually are self-indicating and tell us about the strain and the temperature that these systems experience so that we can try and understand some of the chemistry and physics that exists in the system. Okay. The last thing I want to do is play you this little clip. It comes from The Graduate. Who's seen The Graduate? Okay. You may remember this scene then. For those of you too young, you may not know it, but I thought it was worth showing because certainly within the philosophy of our lab is that what the sentiment of this clip shows is still very true today as it was in 1967. So I'll play this and hopefully the sound is... Do we not get sound on here? There we go. Have I killed the mic? Oh, it's not playing. Oh, anyway, you'll have to watch it when you come down and listen to it down by the stand. What happens in this scene is that this guy, I've forgotten his name, he meets Dustin Hoffman's character at a party, takes him to one side and said, I've just got one word for you, plastics. Plastics is the future. And what I hoped I've showed you a little bit of is the interest that we have in our own group over the last 20 years and how we're moving forward into different areas. And with that, thank you very much for your attention.